In this question, what we've been asked to do is, well, we've got a unidentified compound, and we've effectively been asked to try and work out what is the empirical formula of this unidentified compound. And from the question, we can see it consists of magnesium, carbon, and oxygen. And we've been given the effectively the percentage composition by mass of each of those elements, right? Okay, so how am I going to approach this? Well, in order to be able to compare the elements with each other in terms of the quantity in each, you could say in each molecule of the compound, in order to try and get that down to the empirical formula. What I'm gonna do is I'm gonna try and convert the masses to effectively to moles, so that I can compare them in the molar ratio and work that out. How am I going to do that? Well, the first thing I'm actually going to do is I'm going to just do a quick check and find out what do these percentages actually add up to, right? I'm going to add these together. So in this case, if I add them up, so 28.83 plus 14.23 plus 56.94. So what does that give me? So I would invite you to have a go, see what you get on your calculator from adding these up, right? And if you do have a go at that, what you should get is 100. Right, so they add up in this instance to 100%. Now, sometimes it might not be 100, but in this particular case, it is. Now, from this point going forwards, what I'm actually going to do is I'm going to make an assumption, and this is going to help me to work out the empirical formula. The assumption I'm going to make is that I'm going to assume I've got a particular sample of this compound, and that sample of the compound has a total mass of 100 grams, right? And by making that assumption, I'm able to convert these percentages by mass into actual masses, right? And this is going to be a starting point, because the equation I'm later going to use is going to be the one that relates moles, mass, and molar mass, right? So that's N equals M over MR, right? So that's moles equals mass divided by molar mass, right? Okay, so when we go now to actually working this out, so what we have effectively is magnesium, so Mg. What's the mass of that going to be? So the mass of that's going to be 28.83, okay, grams. For carbon, what's that going to be? So the mass of carbon is going to be 14.23 grams, right? And for oxygen, what is that going to be? For oxygen, that's going to be 56.94 grams. Okay. Okay, so when we now go beyond that, we're trying to now, as I mentioned, we're trying to convert this to molar ratio. So what do we need to do? Well, to get from, as the equation quite clearly states, to get from that to the moles, we need to divide each of these values by the molar masses of the elements, or in other words, the relative atomic masses of the elements in this instance. So let's figure that out. So we need the periodic table for that. So for magnesium, what's that going to be? Let's see here. So you can see that's 24.3 for magnesium, right? For carbon, that's 12, and for oxygen, that's 16. So I'm going to integrate those into what we've got here. So effectively, we're going to divide each of these by their molar masses. So Mg 28.83, divide that by 24.3. Carbon here, we're going to divide that by 12. And oxygen, we're going to divide that by 16. Okay. Okay, so when we do that, what are we going to get in the end? Well, what we're going to get from that is, for magnesium, we're going to get 1.18642, right? For carbon, we're going to get 1.18583, right? And for oxygen, we're going to get 3.55875, okay? Okay, so now that we've got these ratios, we can see that these are not integer values, and what we're aiming for in the cases we're trying to work out the empirical formula, we're looking for integer values, but at least at this stage we have a molar ratio established, right? So what we're going to do now is we're going to look for the smallest value among these, and we're going to divide all the other values by the smallest value, and this should give us at least one whole number. Okay, it should give us at least one whole number. So if you take a look, what we find is, okay, well, this is basically smaller than all the other ones, so we're going to divide all of the other values by that value we have associated with the carbon, so 1.18583, right? So right. So I would invite you to have a go at figuring out what we get when we do all of those divisions, right? Okay, so for magnesium, what do we get? If you work that out for magnesium, what you should get is effectively 1.0050, right? So and for carbon, when you do it for carbon, well, we're dividing a value by itself, so you know you don't need a calculator for that, but you know you're gonna get 1. And in the case of oxygen, this is gonna give us 3.00106. Okay, and when you look carefully at this, what do you observe, right? What do you see? Well, effectively, if you look at all of these to 2 decimal places, all of them are whole numbers, okay? And in other words, they are incredibly close to whole numbers, all of them, okay? So if we actually do that rounding process now, what we're going to get is this is 1.00, that's of course 1, but if I just add the decimals in there, right, just for the sake of it, and then 3.00, right? And so as you can see, because they were so incredibly close to whole numbers, as soon as they were rounded, I mean mainly the magnesium and the oxygen ones, as soon as they were rounded, we've got effectively whole numbers for all of them. And I guess at this stage we ask ourselves, is this the simplest whole number ratio that we can achieve in this particular formula? And reasonably the answer is yes, right? So given that, what we can basically conclude from this is that for magnesium, if there was a number here on, it would be a 1. For a carbon, again, it would be a 1. And for oxygen, it would be a 3. And of course, we don't put 1s on the formulas, so you know what this would be at the end would be MgCO3. Okay, so in this particular case, the empirical formula is MgCO3.